Hello everyone. In this video, I'm going to explain about transistor biasing and stabilization of operating points. To watch more videos, please subscribe to my channel. If you like this video, please share to your friends. Transistors are used in different kinds of circuits. These circuits are meant to serve a specific purpose. For example, a circuit may be used to increase the voltage or power level of an electrical signal. Such a circuit is called an amplifier. So there is another class of circuits which generates sine wave or square wave. So such circuits are called oscillators. So it is very difficult to study all the circuits in which the transistors are used. So however, the study of some fundamental aspects of a transistor circuits may be helpful because the knowledge gained during such a study can help us to understand other difficult circuits also. That is, by using a transistor in the circuit, it may be acts like a amplifier or it may be acts like a oscillator. So here it is very difficult to study all the circuits in which the transistors are used. So here we will discuss some fundamental transistor circuits so that these studying of circuits are helpful to study the other difficult circuits. The first question is, why bias a transistor? So the purpose of DC biasing of a transistor is to obtain a certain DC collector current at a certain DC collector voltage. So these values of current and voltage is expressed by the term operating point. That is, the collector current, that is a DC collector current, and DC collector voltage. So these values of current and voltage are expressed by the term operating point, or we can simply call it as a quiescent point. So to obtain the operating point, we make use of some circuits, and these circuits are called biasing circuits. Of course, while fixing the operating point, it has to be seen that it provides proper DC conditions so that the specific function of the circuit is achieved. The suitability of an operating point for the specific application of the circuit should be seen on the transistor characteristics. So here, biasing of a transistor simply to obtain certain DC collector voltage and DC collector current. So these values of current and voltage is expressed in terms of operating point, nothing but quiescent points. So to make this operating point, or to obtain this operating point, we have to use some circuits. So those circuits are called biasing circuits. So here, to fix the operating point, we have to provide some proper DC conditions so the specific function of the circuit is achieved. That is, if the transistor wants to act like an amplifier, we have to provide some proper DC conditions so that the operating point will be fixed, so that we can achieve that the amplifying action at the outputs. So the suitability of an operating point for the specific application of a circuit should be seen on the transistor characteristics. So here, where we have to fix the operating point, that can be decided at the transistor characteristics. The next question is, where we have to select the operating point on a DC load line. So here, this figure representing the transistor output characteristics. So from the transistor output characteristics, we can see that the major three areas. So one is a cutoff region. So this area is the cutoff region, and second one is the saturation region, and third one is the active region. So when the Q point in the active region, then the transistor acts like an amplifier. If the Q point is in cutoff region, then it acts like a off switch. And when the transistor Q point is at saturation region, then it acts like a on switch. So here, this is the DC load line. So on this DC load line, so when IC equal to 0, here we will get that VCE as maximum as a supply voltage VCC, and when VCE equal to 0, then we can get that the collector current IC equal to VCC by RC. So here when Vc equal to 0, we will get that Ic equal to Vcc by Rc at this point, and when Ic equal to 0, we will get that Vce as Vcc. Then if you add these 2 points by a straight line, then we can call it as a DC load line. So here we have to decide where the Q point we have to fix. That is, certain DC collector current and certain DC collector voltage will decide that the operating point. So for example, here I am taking that 3 points on the DC load line. So here the point A, this is so here this is the point A, which is near to that saturation region, and here point B, which is near to cutoff region, and point C, which is in active region. Now we will give that the input current at the base of the transistor. So how the transistor Q point will be operated. Now we will see what happened if you selecting these operating points locations A, B and C. If you see this figure, the operating point is selected to that near to that cutoff region. So here this is the cutoff region. So here this operating point is selected at point B. So now we will apply that the input base current to the transistor. So here this is the input base current of transistor, a sinusoidal signal. So if you are applying this according to this sinusoidal waveform, the operating point will be oscillated on the DC load line. So here it will be oscillated like this. So it will be oscillated up and down on the DC load line. But what happened here, when the transistor operating point here, when it is enters into that cutoff region, so here this negative cycle, some part will be clipped because the operating point is entered into the cutoff region. That is nothing but the transistor off condition, that is there is no output at the cutoff region, so that the negative cycle will be clipped. That is nothing but there is no voltage and currents at cutoff region. That is when the transistor operating point is at cutoff region. So like this, the negative cycles will be clipped, so that the distortion will be occurred when the transistor operating point is selected to that near to that cutoff region. So next, if you are going for, if the transistor is selected nearer to the saturation region, so according to the base input, there is nothing but for a given sinusoidal input at the base of the transistor, here the operating point will be oscillated like this. According to the given input, the operating point will be oscillated. So but the operating point is when it is in that saturation region, according to the given input, the positive cycle will be clipped because the operating point is entered into the saturation region. When it is entered into the saturation region, then there is no output. That is, the positive cycle will be here, it is clipped. That is nothing but the distortion will be occurred at the outputs. And next, if you are going for the transistor operating point at the middle of this active region, that is at the middle of this active region, then for a sinusoidal applying at the base input, then the transistor Q point will be operated like this. So these oscillations will be done within the active region only, so that there is no distortion will be occurred. So the selection of the operating point should be at the middle of this DC load line, so that there is no distortion at the output. And if you see this one, the transistor operating point is selected at the middle of the DC load line, but the input given here, it is a very large signal. So what happened? So this part will be entered into the cutoff region, and this part will be entered into the saturation region. So there is no outputs at saturation region and cutoff region. So here there will be a clipping of positive and negative cycles. So here there will be a clipping of positive and negative cycles. From this we can know that the transistor operating point should be at the middle of this active region on the DC load line, and at the same time the input signal should not be a large signal, so that we will not get the distortion at the outputs. So like this we have to select the operating point of a transistor. So the next one is need for bias stabilization. So here only the fixing of a suitable operating point is not sufficient. It must also be ensured that it remains where it was fixed. That is, once the operating point is fixed on the DC load line, the position of the operating point should not be changed. So it is unfortunate that in the transistor circuits, the operating point shifts with the use of the circuit. That is, when you are using the circuit, automatically the operating point may be shifted by using of the circuit. So such a shift of operating point may drive the transistor into an undesirable region. That is, the operating point may be shifted to saturation region, or it may be shifted to cutoff region. So when the operating point shifts like that, the amplifier becomes useless. So there are two reasons for the operating point to shift. Firstly, the transistor parameters are temperature dependent. Secondly, the parameters change from unit to unit. That is nothing but the transistor beta value. So here the operating point may be shifted on the DC load line near to saturation region or near to cutoff region because of two reasons. One is the transistor parameters are temperature dependent. That is, when the temperature increases, maybe the transistor operating point may be shifted, or if you are changing the transistor by another transistor within the circuit. So for example, a transistor is damaged in the amplifier circuit, so you replace that damaged transistor by another new transistor, but the beta value of the transistors are different, so that due to changing of this beta value, the operating point may be shifted. So these are the main reasons to shift the operating point to undesirable region. So when the transistor is replaced by another of the same type, the operating point may be shifted. So such problems do not arise in case of vacuum tube circuits. That is, here for the transistor we have beta value is there. So the beta value will be changed from one transistor to another transistor. So when you are replacing the transistor by another transistor, then what happened? The beta value automatically changed, so that the operating point may be shifted. But this problem is not arised in vacuum tube circuits. So generally, when the flow of current in the collector circuit produces heat at the collector junction, so this increases the temperature, so more minority carriers will be generated at the collector base region. So due to this one, we have the leakage current ICB0 will be increases. So already we know that the leakage current can be represented in the CE configuration as a ICE0 equal to 1 plus beta into ICB0, and we know that the collector current of the CE configuration is given as IC equal to beta IB plus ICE0. So when the temperature increases, more minority carriers will be generated at the collector base region, so this will increases that the leakage current ICB0. From this, the collector to emitter leakage current can be represented as, so from this we can represent ICE0 equal to 1 plus beta into ICB0, and the collector current IC equal to beta IB plus ICE0. So flow of current in the collector circuit produces the heat at the collector junction. So this heat will increases the temperature at the collector junction. So when the temperature increases, more minority carriers will be generated at the base region, that is nothing but at the collector base region, so that the leakage current will be increases. So that leakage current is given as ICB0. So from this we can write the collector to emitter leakage current ICE0 equal to 1 plus beta into ICB0, and at the same time the collector current IC is given as beta IB plus ICE0. So generally this process we can call it as a thermal runaway. So here when the temperature increases at the collector junction, then the leakage current will be increases, that is the ICB0. So when the ICB0 increases, ICE0 will be increased. When the ICE0 increases, then the collector current IC will be increases. That is, when the collector current increases at the collector junction, again the temperature will be increased. That is nothing but here the temperature T is increased. When the temperature T increases, then again ICB0 increases, IC0 increases, again IC increases. So this is a cumulative process. And finally the junction temperature, that is the collector to base junction temperature, will be increased very high value, so that the transistor will be burned out. So generally we can call it as a thermal runaway. So then what are the requirements of a biasing circuits? So establish the operating point in the center of the active region of the characteristics, so that on applying the input signal, the instantaneous operating point does not move either to the saturation region or to the cutoff region, even at the extreme values of that input signal. And the second one is stabilize the collector current against the temperature variations. That is, if the temperature is varied, then automatically the operating point may be shifted. And make the transistor independent of the transistor parameters, so that it does not shift when the transistor is replaced by another of the same type in the circuits. So these are the requirements of the biasing circuits. So here we have different biasing circuits are there. So the figure shown in this slide is a simplest biasing circuit. So the emitter base junction is forward biased by the battery VBB, and the collector base junction is reverse biased by the battery VCC. So the voltage VBE across the forward bias junction is very low, that is, for a germanium transistor VBE equal to 0.3 volts, and for silicon the VBE equal to 0.7 volts. This requires that the battery voltage VBB must also be of the same order, that is nothing but the battery voltage VBB should be 0.3 volts or 0.7 volts. And the collector base junction is reverse biased, so that we need some voltage like 6 volts. So here, when the transistor input section is forward biased and when the transistor output section is reverse biased, then the transistor will be in the active region. But forward biasing of the emitter base junction and reverse biasing of the collector base junction, it is not a practical circuit. So it is extremely difficult to have a battery VBB of either 0.3 volts or 0.7 volts. So that this circuit therefore is never used. So here we will not get the battery voltage as 0.3 volts or 0.7 volts in the market. It is very difficult to get this type of a battery of voltage 0.3 volts or 0.7 volts. So it is not possible. So this circuit is not used. So for this one, a modified circuit is introduced. So generally we can call that circuit as a fixed bias circuit. So here in this circuit, the battery VBB need not to be of low value, that is 0.3 volts or 0.7 volts. So when current IB flows through the series resistance RB, a major portion of the voltage is dropped across it. That is, here the voltage will be dropped across the RB resistance. So the supply voltage VBB can be now be of 1.5 volts. So such a supply voltage is easily available at markets. So it is interesting to note that the same circuit can also be drawn in a different way. That is, here, so this is the circuit we have, this is the resistance RB. So the major portion of the voltage drop will be across that RB, so that the battery voltage 1.5 volts will be easily available at the markets. So here this circuit can be drawn as differently, that is, here this can be represented as VBB plus VBB, and this can be represented plus VCC. Through the resistance RB and RC, they are connected to this transistor. So here in the previous image, there we are using two batteries, VCC and VBB. So the positive terminals of both the batteries are connected to the collector and base transistor. So we can use a single battery instead of these two batteries. So as shown in here in this figure, so here it is connected to this single supply voltage instead of by using VBB and VCC. So the value of RB is then suitably modified. From a practical point of view, it is always preferable to have an electronic circuit that works on a single battery. That is, here instead of using two batteries, here we will use only a single battery. So according to that one, we will select these RB and RC values. So here the supply voltage VCC is fixed and the resistance RB is fixed, so that the base current IB is also fixed. So generally we can call it as a fixed bias circuit. So now we will see that the input section. So let us first consider only the input section of the circuit. So here it is shown in this figure, this is the input section. So here VCC and RB and the base terminal of the transistor to the emitter terminal. So here it is the input section, so VCC and RB and the base to emitter terminal. So if you are representing like this, the same circuit, so here this VCC and the base current IB is flowing through the resistance RB, and here the voltage drop across the base to emitter terminal is considered as VBE. So applying that, the Kirchhoff law, then VCC equal to, here VCC equal to IB into RB plus VBE. So from this we can represent this IB equal to VCC minus VBE by RB. So by doing simple mathematical manipulations, here you will get this IB equal to VCC minus VBE by RB. So here this voltage drop across this base to emitter terminal is very less, so that we can represent the base current IB is equal to VCC by RB. So here this resistance RB is fixed and this VCC is fixed, so that the base current IB is also fixed. So here this VCC is fixed and RB resistance is also fixed, so that the base current IB is also fixed, so that we can call this circuit as a fixed bias circuit. And next we will go for the output section. So when you are going for this output section, here we have that VCC equal to the current flowing through this resistance RC, IC into RC plus collector to emitter voltage drop VCE. So IC equal to, we can write this one as VCC equal to IC RC plus VCE. So here it is the equation we have. So VCC equal to IC RC plus VCE. So already we know that the collector current IC is equal to beta IB plus ICE naught, where ICE naught is nothing but the collector to emitter terminal leakage current when the base terminal is opened. So this equation already we know that IC equal to beta IB plus ICE naught. So here if ICE naught is a very small value, then we can write this one as IC equal to beta into IB. So in this equation here VCC equal to IC RC plus VCE. So if VCE is very small, then we can write this one as VCC equal to IC RC. But here the voltage drop across this resistance RC, which is always less than VCC, so that we can represent this IC is less than or equal to VCC by RC. And at the same time this VCE can be represented as VCC minus IC RC, and IC saturation is equal to VCC by RC. So here by using this VCE and IC saturation values, we can determine that the operating point of this fixed bias circuit. So this fixed bias circuit is not used generally, but here this fixed bias circuit is a simple circuit. It uses very few components, only 2 resistors and 1 battery. So it is very easy to fix the quiescent operating point anywhere in the active region of the characteristics by simply changing the value of the resistance RB. So it provides maximum flexibility in the design, but it is not used. Why? Because so here the resistance RB value is fixed, then the base current RB is also fixed. So when the temperature rises, so there will be a cumulative action takes place and the collector current goes on increasing. So the circuit provides no check on the increase in the collector current, so that the operating point is not stable. So this situation can be shown in this figure here. So when the temperature T increases, then ICB naught increases, and if ICB naught increases, then ICE naught increases, then IC increases. Again, if the collector current IC increases, then at the junction the temperature T again increases. So like that, if the temperature T increases, again ICB naught increases, again IC naught increases, again IC increases. So if IC increases, again the junction temperature will be increases. So this leads to thermal runaway, so that the transistor simply burned out. So that this fixed bias circuit is not used for transistor biasing. So we will go for another circuit. So that circuit is a collector to base bias circuit. So here there is a connection from the collector terminal to that base terminal through the resistance RB. That is why you are calling this as collector to base bias circuit. So here this is the circuit of that collector to base bias circuits. So if you see this one, here we have VCC is there, here we have the collector resistance RC is there, and the current flowing through this resistance RC is considered as IC plus IB, because at this node the current is dividing as IC and IB, and the collector current here we have that IC is there, and the base current is IB is flowing through the resistance RB here. Okay, so when you're going for that input section, we have that VCC equal to IC plus IB into RC plus IB RB plus VBE we have. So like this. So here we will get that like this. So VCC equal to RC into IC plus IB plus IB RB plus VBE, and from this you extract the correct component, that is the base current IB here. Okay, then IB equal to VCC minus IC RC minus VBE by RC plus RB you will get. Okay, so this is about that input section side. We got that base current IB, and when you're going for that output section here, you will get that VCC equal to RC into IC plus IB plus VCE you will get VCC equal to. So from this you extract this VCE, that is that the collector to emitter voltage, then you will get that VCE equal to VCC minus IC plus IB into RC. But here this base current IB is less than this collector current IC, so we can neglect this one, so that we can get that VCE equal to VCC minus IC RC. So here if you are substituting this equation, that is VCE is approximately equal to VCC minus IC RC, in this equation that is nothing but here you will get that VCC minus IC RC. So here we have that VCC minus IC RC, this is nothing but here we have that VCE, then IB equal to VCE minus VBE by RC plus RB you will get. So this is the base current IB. Okay, so but this circuit is not used. Why? Because here we have, when the temperature T increases in the collector to base bias circuit, that ICB naught increases. When the ICB naught increases, IC naught increases. So when the IC naught increases, then the collector current IC is also increases. So here when IC increases here, then VCE will be decreases. So here we have that equation is there. In this equation, in the output section equation, here we have when that IC increases, here automatically VCE decreases. So when that VCE decreases, here, then automatically IB is also decreases. So when the IB decreases here in this equation, when the IB decreases, then the collector current IC is also decreases. So here this collector to base bias circuit is making the transistor independent of the temperature. That is, even if the temperature increasing, the collector current IC is maintained as constant. But here this circuit is not used. Why? Because so this circuit has a tendency to stabilize the operating point against the temperature and beta variations generally. But the circuit is not used very much, because the resistor RB not only provides a DC feedback for a stabilization of operating point, but it also causes an AC feedback. That is, the resistance RB will provide a DC feedback, but also it provides that the AC feedback. So this reduces the voltage gain of the amplifier. So this reduces the voltage gain of the amplifier. So it is not desirable. That is, the voltage, when the voltage gain of the amplifier is decreasing, it is not desirable. So that is why this collector to base bias circuit is not used in biasing of a transistor. So this is the main drawback of that collector to base circuit. So in order to find out that the operating point for this collector to base bias circuit, so here already we know that this equations VCC equal to from this equation we know that, so VCC equal to RC into IC plus IB plus IB RB plus VBE. So we know that equation. So here in this equation just substitute beta IB for IC. That is, here in the place of IC we will substitute that beta IB, so that we get the equation. So VCC equal to RC plus beta IB plus RC plus RB into IB plus VBE. So from this we will get VCC equal to VBE plus RB plus beta 1 plus into RC through whole IB, that is product of this IB. So from this you will get that IB equal to VCC minus VBE by RB plus beta plus 1 into RC. So if you are approximating this, that is the base to emitter voltage is a very less value, then we can write this IB equal to VCC by RB plus beta into RC. So we know that the IB then we can write that the collector current IC equal to beta into IB. So now we got that the collector current IC. So now we have to find out that the collector to emitter voltage VCE. So this is the equation, already we know that. So VCC minus IB plus IC into RC minus VC equal to 0. So from this we can write VC equal to VCC minus IC plus IB into RC. This can be approximated as VCC minus IC RC because the base current is very less than that of IC. So we can neglect that one. So we got that collector current IC is there, and there is nothing but collector current saturation current, and here we have that VCE on that DC load line. So like that we can find that operating point for this collector to base bias circuit. So the next circuit is that bias circuit with emitter resistance. So here already we seen in that fixed bias circuit. So for this fixed bias circuit, the additional resistance RE is connected. So here we apply that some Kirchhoff voltage law, so that we get that VCC equal to IB RB plus VBE plus IE into RE. So this is applied for that input section. So from this equation we can get IB equal to IE RE minus VBE by RB. So when the VBE is a very less value, then we can approximate this IB equal to VCC minus IE RB by RB. So because this VB is very small, so from that input section we got that the base current IB equal to VCC minus IE RE by RB. So this bias circuit with emitter resistance is making the independent of the temperature and at the same time the beta value. So if you see this one here, if the temperature T increases, ICB naught increases, then ICE naught increases, then collector current IC increases. So when the collector current IC increases, then automatically the emitter current IE is also increases. So when the IE increases, then the current flowing through this resistance RE is also increases. When this increased, that is IE RE, that is the voltage drop increased across the RE, so that the base current IB decreases. So when the IB decreases, then automatically the collector current IC decreases. So like that, this bias circuit with emitter resistor is making the collector current IC independent of the temperature. But here this circuit is not used in the transistor biasing. Why? Because if you see this equation, IB equal to VCC minus VB by RB plus beta plus 1 into RE. So if you are approximating this equation as IB equal to VCC by RB plus beta RE, so when VB is neglected. So already we know that the collector current IC equal to beta into IB. So when the beta is substituted in this IB current equation, then we can get this VCC by RE plus RB by beta. So if you see this equation, here the resistance RE, here the resistance RE is far greater than that of RB by beta. Here from this equation we can say that the resistance RE is far greater than that of this RB by beta. So a high value of RE will cause a large DC drop across it. That is, here the high value of this RE, there will be a large voltage drop across it. So to obtain a particular operating point under this condition, it will require a high DC source of VCC. So on the other hand, if RB is low, a separate low voltage supply has to be used in the base circuits. So both the alternatives are quite impractical, so we should not use this circuit in transistor biasing. So but this circuit, this bias circuit with emitter resistance, making the transistor independent of this temperature and at that beta variations. So here when the beta increases, when the transistor replaced by another transistor, this beta value will be increases. When the beta value increases, then the collector current IC increases. When the collector current IC increases, then automatically the emitter current IE increases. So when the IE increases, the voltage drop across the resistance RE will also be increases. So when the IE RE increases, then automatically the base current IB decreases. So if the base current IB decreases, then automatically the collector current IC is also decreases. So like this, the collector current IC will be maintained as constant even if the transistor is replaced by another transistor. But here it is not used. So these are the equations to get the operating point of this bias circuit with emitter resistance. So here we got that the collector current IC, and by applying that Kirchhoff voltage law to the output circuit of this bias circuit with emitter resistance, then we will get that VCE equal to VCC minus RC plus RE into IC. So here why you are taking this as IC, as because this IC is approximately equal to IA. So these are the current and voltages to determine the operating point of this bias circuit with emitter resistor. And next one, the last one, voltage divider biasing circuit. So here this is the most widely used biasing circuits. So it is shown in the figure. So here it is the figure of this voltage divider bias circuits. So compare this circuit with so here when you are comparing this voltage divider biasing circuit with the previous circuits, here we have that bias circuit with emitter resistance. Here we have some additional resistor is connected between the base and the ground. So here this is the additional resistance which is connected between the base and the ground. So the name voltage divider comes from the voltage divider formed by the resistances R1 and R2. So by suitably selecting this voltage divider network, the operating point of the transistor can be made almost independent of beta and against the temperature variations. So this is why this circuit is also called as biasing circuit independent of beta. So now we will go for this voltage divider biasing circuit with the approximate analysis. So to determine the operating point, we first consider the input section of this circuit. So here this is the input section of the circuits. So here we make some basic assumptions. So the base current IB is very small compared to the currents in R1 and R2 resistances. That is, the current I2 and I1 are much greater than that of this base current IB. So this is the basic assumption we considered. So here this I1 and I2 is far greater than this base current IB. This is the basic assumption we considered. The above assumption is valid because in practice the resistance seen looking into the base, that is nothing but the resistance into the base, that is nothing but the input resistance Rin, is much larger than R2. So we can apply the voltage divider theorem to find the voltage across the resistance R2. So same as the voltage VB. So here in this circuit we are representing the some theorem, voltage divider theorem. Here we have, so here we have VCC is there, the resistance R1 and the resistance R2, and this is the base current IB. So across the resistance R2 we have the voltage drop as V2, and the resistance R2 and the current flowing through this resistance R2 and the current flowing through this resistance R2 is given as I2, and the current flowing through the resistance R1 is given as I1, and that is looking into the NPN transistor, then the input resistance Rin is given as 1 plus beta into Ra. So now coming to this voltage V2, here we have, so here we have voltage V2 is there. So now we will find out that voltage V2, that is nothing but the base voltage VB. So it is given by the resistance divider formula, that is R2 by R1 plus R2 into VCC. And here we know that VE equal to, that is the voltage drop across the emitter terminal equal to, so here the voltage drop across this emitter terminal is given as, we have V2 minus VBE, that is, this is the voltage drop across this base terminal. So then V2 minus VBE, then we will get that VE, and the emitter current IE is given as VE by RA. So from this we can write that VE as V2 minus VBE by RA. So this is the emitter current we got here, and the collector voltage VC is given as VCC minus IC RC. So then we will get that the collector voltage VC, and we know that the collector to emitter voltage VC is given as VC minus VE. Then if you substitute this VC and VE in this equation, then you will get that VC is approximately equal to VCC minus RC plus RE into IC. So this is the collector to emitter voltage VCE. This will decide that operating point on the DC load line. So here we got that VCE, and here the collector current IC is approximated with this emitter current IE. So that we have that collector current IC is now available, and the collector to emitter voltage is also available, that is nothing but VCE, so that we can decide that operating point of the transistor on the DC load line. Now we will go for the circuit analysis of this voltage divider biasing circuit. You may be wondering why the operating point does not change when the transistor is replaced by another. So here in the circuit already we shown that the voltage divider bias circuit. So here this is the voltage divider bias circuit. So it is really so to verify this circuit will make the transistor independent of temperature T and the beta value. So now we will see how this voltage divider biasing circuit will make these two parameters independent. So here we have a complicated network containing resistors and voltage sources. For example, so here we have a complicated network containing resistors and voltage sources, that is shown in the figure like that. So A and B are the two terminals in this network. Then the Thevenin's theorem simply states that this circuit acts as if a voltage VThevenin in series with a resistance RThevenin is connected in between that pair of terminals. So now we can analyze this voltage divider biasing circuit by considering simple Thevenin's theorem. Suppose we have a complicated network containing resistors and voltage sources. So here A and B are the two terminals in this network. Thevenin's theorem simply states that this circuit acts as if a voltage source VThevenin in series with a resistance RThevenin is connected in between this pair of terminals, that is A and B. So now when we connect the resistance RL across the terminal A and B, only one loop is seen. So it becomes very easy to calculate the current in that resistor. The power of the Thevenin's theorem lies in converting the complicated network into the simple loop circuits. So the Thevenin's equivalent voltage source VThevenin is the open circuit voltage across the terminals A and B. The Thevenin's resistance RTh is the resistance from A to B when all the sources in the network are reduced to 0. That is nothing but here we will make the short circuit, so that we will get that RThevenin's value of the circuits. So after Thevenizing the circuit at A and B terminals, we may connect any resistor across A and B and calculate the current flowing through it. So the voltage divider biasing circuit is shown in figure. Here we have. So let us Thevenize the circuit on the left of the terminals A and B. So here we have that. Terminals A and B is there. So this is the left, and here we have the right. So let us Thevenize the circuit on the left of the terminals A and B. So the result will be, you will get VThevenin equal to R2 by R1 plus R2 into VCC. So the resistance RThevenin is found by reducing the battery VCC to 0. So here we will make this VCC to 0 and calculating the equivalent resistance between the terminals A and B. When VCC is shorted, the two resistors R1 and R2 are in parallel, so that we can represent this RThevenin as of these two resistors R1 and R2 as R1 into R2 by R1 plus R2. So we got this. Okay, so we shall now analyze the circuit which is shown in this figure. So for the calculation of that operating point, here we require VCE and IC we require to calculate the operating point. So from this above figure we got that VThevenin is equal to IB RThevenin plus VBE plus IE RE. So from this we will get that VThevenin, and also for that input section, if you apply that Kirchhoff voltage law, then IB equal to VThevenin minus VBE by RThevenin plus 1 plus beta into RE. So this is approximated with the VThevenin by RThevenin plus beta RE. So this beta is approximately closed with that collector current IC. So IC equal to beta into IB. And from that output section we can get that VCE equal to VCC minus RC plus RE into IC. So like this we can calculate that the operating point of that transistor. So here by using this voltage divider biasing circuit, here this circuit will make the transistor independent of the temperature and beta values. So thank you very much for watching this video. To watch more videos, please subscribe to my channel Open Box Education. So if you like this video, please share to your friends also.